Good morning, guys. Unfortunately, my baby daughter is still very sick and I'm gonna have to take over today. But I decided that I have a few minutes to do a small video on what's called the mean value theorem. It's one of those isolated lessons that really could be taught anywhere. It doesn't really have a belonging in one particular unit, so I figured today would be a good day to do that. So you're gonna get out some pen and paper and work along with me. And of course, if you have to stop the video at any time to catch up or process what I'm talking about, then feel free to do that. So you're going to start off, we've drawn this diagram before for a couple of other theorems, a small snippet of a function, and you're going to identify the domain endpoints as a to b, like I have here. So basically what the mean value theorem says is, first and foremost, if you're working with a differentiable function on a domain a to b, so we have to just review what differentiable implies. First and foremost, differentiable does imply continuity. So you have to be working with a continuous function. So we're not going to be seeing any points of discontinuity. We don't want to see any asymptotes on our given domain a to b. Continuity is not enough though. Differentiable also implies that the left-hand limit of f prime of x is equal to the right-hand limit of f prime of x, which essentially means, you're not working with corners, cusps also, which we don't here. We can see that we have a smooth snippet of a polynomial function, so we are safe to go for mean value theorem. If we did have a corner or a cusp, then we could not apply the mean value theorem. So getting to what the theorem is really about, after talking about those prerequisites that we just did, it essentially says this, that if you were to draw a secant line connecting your domain endpoints A and B, that there exists at least one location in between A and B for which you could draw a tangent line that would appear to be parallel. So I'm just going to estimate that that might be, I don't know, right about here. We're just really eyeing this out. And the mean value theorem calls that location C. And if I draw my tangent line to the best of my ability, yeah, it's pretty good. Hopefully you can see that the secant line and the tangent line do appear to be parallel. And sometimes there's more than one location where that can happen. In the diagram that I drew, there was only one location where you could draw a parallel tangent line to that secant line, but keep in mind that there could be more than one location depending on what the function looks like. And again, that's really the premise of the mean value theorem. So this requires for us to set up a formula, basically, which we will be able to do because we've already learned how to find the slopes of secant lines, and we know how to find the slopes of tangent lines as well. We just have to sort of connect the two ideas together. So back in the day, a couple of months ago, when we learned about the slope of secant lines, we just used the slope formula, y2 minus y1 all over x2 minus x1. Being that I'm not using x1 and x2 notation, that I'm using a and b notation, I'm going to switch over to the f of b, f of a format as opposed to y2 minus y1. So the slope of the secant line we could represent as f of b minus f of a. So something to that effect. Now, if these lines are parallel, we do know that the slopes are the same. So this slope of the secant line is equal to the slope of this tangent line. And being that it is a tangent line and we're talking about the slope, we are talking about a derivative, right? So we're going to represent the slope of this tangent line as f prime of c, right? The slope of the tangent line at the x value c. And there you have it. There's your formula for the mean value theorem. So in my next small video, I'm going to do an example with you, and then you have just a couple of delta problems that I would like you to work on today.